All right. So let's begin. We started talking about auctions last class, and we're gonna keep talking about auctions for a little bit, sort of a mini section of the course. And maybe just to remind ourselves of where we are. So last lecture, we introduced this extremely general mechanism design setting, just to like jog your memory a little bit. There's like a completely arbitrary set of choices that we need to make. Like we just called this the set of alternatives, and participants in the auction could have entirely arbitrary set of preferences, valuation functions, mapping arbitrary alternatives to valuations, and assuming that they have quasi-linear utilities for money, which just means they can represent, their happiness level for all of the different alternatives we might choose in units of dollars, and that their value for money is linear in the amount of money. We showed that there was this one mechanism, the VCG mechanism, that solved this problem like in full generality and had a lot of nice properties. It maximized social welfare. It was individually rational, which means that sort of it was safe for people to participate. They would never be asked to pay more than they valued the alternative that was chosen. It was dominant strategy truthful. Nobody could manipulate by sort of misrepresenting their preferences. And it had the no deficit property. Like we were going to make money, we weren't going to lose money. Okay, so this general setting captured all sorts of stuff, not just single item auctions that were sort of our running example. I have a thing to sell, who's it going to go to? But really lots of things in full generality. It could be arbitrary combinatorial auctions where we're giving out lots of stuff and we've got constraints about who can get which subsets. For example, if we were auctioning off takeoff and landing slots at airports, or if we were auctioning off radio spectrum across the United States, just to mention a couple of real world examples. It could capture public projects problems. Should we, as a town, build a fire station or, a library? So all sorts of things. And we sort of ended the class, wondering if, like that was it. It's like maybe you don't need auction theory beyond the 1970s when the VCG mechanism was developed. Like maybe that just solves mechanism design. And there were a couple of reasons we had at the end of class for why we might not quite be done. One that I'll just remind you of, but is not the topic of today's lecture, is computational complexity. So we just sort of took it as given that we could say, all right, just choose the alternative that maximizes social welfare given the reported valuations. But of course, in a complicated setting with a big outcome space, that might be a computationally hard problem, and we'll have to spend time later in the class thinking about what to do when it is. But sort of more immediately, and what we'll talk about today, is that the VCG mechanism was great if the thing you wanted to do was maximize social welfare, right? Like if what you wanted to do was choose the alternative that made people in the aggregate as happy as possible. You had this sort of utilitarian objective where you just want to maximize average or some value for the alternative chosen. Well, that's exactly what the VCG mechanism does. But we might find ourselves in a position where that, social welfare is great and all, but maybe that's not our goal. Maybe we have some other objective we'd like to maximize. For example, an objective you often want to maximize when you're selling things is you want to maximize your revenue or your profit. Okay, and the VCG mechanism it doesn't do that. It's very specific to maximizing social welfare. So what I want to do today is to, the general problem of understanding all of the objectives that are compatible with dominant strategy truthful mechanisms in the full mechanism design setting as we defined it last class. That's a complicated problem that's still not completely understood. But what you can do is when you sort of restrict your attention to restricted classes of problems that still capture some interesting stuff, you can fully characterize, fully answer this question: what objective functions can you optimize for in a dominant strategy truthful way? So that's what we're going to do today in a particular class of problems that I'll define called single parameter domains. We'll give sort of a full classification for when you can solve this problem and when you cannot. And this will be sort of the basic building block that we use next class, or for the next few classes really, to do a few things. One of which is maximizing revenue in the class of auctions, another of which will be solving various kinds of combinatorially hard auction problems that require the design of approximation algorithms with special properties. What those properties are will be sort of the content of today's lecture. Okay, so that's sort of the agenda for today. Questions about the plan of action before we dive in? Okay, so like one thing I want to observe, like the VCG mechanism, it maximizes social welfare, which is just the sum of the valuation function, like the unweighted sum of the valuation functions for the alternative chosen. One easy extension that is something you're gonna prove on the next homework is that very similar ideas, very similar derivations actually will allow you to maximize like a slight generalization of the social welfare function, which basically amounts to like weighted social welfare. Like you don't have to maximize the unweighted average of everyone's happiness for the alternative chosen. You could maybe like some people better than others, some people are more important than others. You could give different people weights and you could maximize the weighted average. And in fact, you might have your own preferences as the mechanism designer, so you could give weight to to your own preference. If you want to put your thumb on the scale. So you could take the social welfare objective and sort of maximize instead like an affine transformation of that, where I differently weight people's values, and maybe I have preferences myself as the mechanism designer. So this is a pretty easy extension of what we did in class last time, and you'll do it on the homework. But this isn't a huge extension. These things all really look like social welfare. So the real content of this class is, what else we can do? What are things what are objective functions we can maximize, which like really don't look like social welfare? How far can we get beyond this? And as I suggested earlier, like in full generality, that's kind of a hard problem. I mean, yeah, even at the research frontier, this is not a fully understood problem in full generality. So we're not gonna answer this question in full generality of what objective functions can we maximize in a dominant strategy truthful way in arbitrary mechanism design problems, but rather we'll try to like give a complete answer for that question in a restricted domain that is still rich enough to have some interesting stuff in it. And this restricted domain, in this restricted setting, is something I'm going to call a single parameter domain. And I'll walk through the definition, but let me try to give some intuition first. So remember, in full generality, in this mechanism design setting, we talked about last time, you could really have an arbitrary valuation function that just assigns like an arbitrary real number to each of the possible alternatives. So like the number of parameters I would need to write down your valuation function is linear in the number of alternatives. Like you need to be able to tell me how happy you are for every possible alternative. So for example, in a combinatorial auction with k items, you would need to tell me not just your utility for all of the different subsets of items that you might get, but in principle, you could also have preferences over the subsets of items that other people get, right? Like maybe you'd be jealous if your next door neighbor got like a cool car or something. Similarly, right, even just like in like a single item auction, which seems like this sort of super simple thing. When we analyzed it last class and we sort of noticed that like second price auctions are truthful, we assumed that you didn't care, like we assumed that the only thing you cared about was whether you got the item or not, right? Like there was some value you had for this item such that if you got it, you would experience, V units of happiness. And if you didn't get it, you'd experience 0 units of happiness. But if you didn't get it, you didn't care about who else got it. But that was an assumption. In the generality in which we defined the mechanism design problem and in which we proved the VCG mechanism has nice properties, you could have, right? Like you could have had in principle a different utility for every single person who might be allocated the item. Okay. So informally, single parameter domains are those for which we assume that's not the case. Like basically, we assume that for everybody, there is a publicly known ordering over outcomes. For example, in a single item auction, we assume everyone would prefer to get the item over not getting the item. And we assume everyone is indifferent to who gets the item, assuming it's not them. Okay, so the thing that we sort of just assumed structurally about people's preferences is that they'd prefer to win the item than to not win the item, at least if prices are no objects. And that assuming they do not win the item, they don't care who else wins it. And that's what we assumed last class. And what we got out of that was that I could describe your utility function in this case, which otherwise could be like a complicated object, just with like a single number. What is your value for the item, right? Like how happy are you going to be in the event that you get the item? Okay, so a single parameter domain just sort of generalizes this. We sort of assume, like, we say, okay, look, we've got some set of alternatives A, but what we assume is publicly known is what I'll call, for every agent, a public value summarization function that maps alternatives to real numbers. That's sort of like the relative, the sort of assumed relative preference over all of the outcomes. Like you prefer winning the item to not. So maybe this public value summarization function maps to 1 in the outcome in which you win the auction and maps to 0 for any other outcome. Okay, so that's sort of some structural assumption about your preferences that we assume we don't need to elicit from you. We know that already. You prefer winning the item to not. The only thing we don't know is like quantitatively how happy you're going to be if you win the item. Okay, so this public value summarization function, this is publicly known. We don't need to like elicit this through a truthful mechanism, but there's some like number, there's some real number VI, like your value for the item that we don't know, that is like a scaling factor. Your happiness at some alternative A is going to be VI times this public value summarization function. So just to like make that concrete, to walk through a couple of examples. Single item auctions are a single parameter domain. And the public value summarization function is just what we've been talking about. It says your relative utility for winning the item is 1, and your relative utility for losing the item is 0. And of course, there's this unknown scaling factor, V, your value for the item, and your actual value for winning the item will be V times this. So it'll be V if you win the item and 0 otherwise. Right, so by assuming this structure, by assuming that you don't care who gets the item, assuming it's not you, what this lets us do is it lets us summarize your otherwise complicated valuation function in like a single number, your value for the item. Doesn't have to be a single item auction either. It would sort of work in a combinatorial procurement auction as well, in some settings. So let's consider the following mechanism design setting. We're here, maybe the mechanism designer is not selling things. The mechanism designer is buying things instead. We could call this a procurement auction. And suppose that what the sort of mechanism designer wants to buy are paths in a network. Maybe the mechanism designer would like to buy a path in the network that connects some source to some sink. And maybe the agents correspond to edges in the network. So the agents correspond to service providers who can route traffic from point A to point B. And right. So what the mechanism designer is going to have to do is it's going to have to sort of buy from a subset of agents corresponding to a path connecting point A to point B to optimize some objective. But the agents are going to experience cost if they provide the service. So I'm an agent that controls some edge. If I am going to let you use the edge, then I will experience some cost. Now, you don't know what that cost is. That's the thing that you need to elicit truthfully if we're going to have a truthful mechanism. But like maybe what is known is that the structure of that cost function is that the agent controlling some edge will experience some cost if the bundle we buy is a path that includes that edge, and they will experience no cost otherwise if we don't have to use the edge. Okay, right? So the alternative chosen is going to be a subset of the edges, and agent E, corresponding to one of the edges, will have some cost if the edge is in the bundle and won't otherwise. This is the public value summarization function. Now, quantitatively, we don't know what that cost is. That's the thing that we need to truthfully elicit in the mechanism design problem, but that can be summarized as a sort of just a single parameter, like a scalar equal to their cost that'll just be multiplied by this to figure out what their cost function is. Some unknown cost CI if their edge is used and zero otherwise. Okay, so this is also a single parameter domain because the thing we need to elicit is just a single number. The relative ordering of the outcomes in all of the agent's preferences is known. Just maybe for one more example, suppose what I'm doing is I'm selling advertising slots. Okay, so maybe I've got like banner ad slots that I can fill with your banner ad, and I've got real estate on different websites. So you could buy a banner ad on the New York Times website, or the Washington Post website, or the Fox News website. And suppose I know that what the agents have is like some utility that is like additive in the number of unique viewers who see their ad. Okay, so maybe like, they're selling something. So every time I show the ad to like a new person, they have some chance of clicking through and buying the thing for me. So for each person, like given how effective my ad is and how expensive my product is, I make, I don't know, maybe 6 cents. But that I don't have any value for showing the ad to the same person the second time. Like the ad's going to work or it's not. Okay, so for a bidder in this auction who's going to get, who's going to get like an allocation of ad slots as the alternative chosen by the mechanism, what they care about is, if every ad slot corresponds to some set of viewers, what they care about is the cardinality of the union of those sets. Okay, so maybe if the Washington Post and the New York Times, right, they might like individually have lots of viewers, but maybe they have a lot of viewers in common. And so the bidder would have high value for either one of those ad slots on its own, but their value for the union of the two of them wouldn't be that much higher. Whereas maybe their value for like the New York Times and Fox News would be higher because even if the sets themselves are comparable size, they're much more disjoint. So the union would be large. Okay, now, if I made that assumption that the thing that the advertiser cares about, that the advertiser's utility is basically some scalar multiple, like some kind of click-through rate of the number of unique users, then the complicated part of the utility function, which is that what you care about is the union of the advertisers who are going to, or the users who are going to view your advertisement across the bundle of slots you get, that part I can sort of shove into this public value summarization function. And the only thing I need to elicit from you is like this real number V, which is exactly how many cents each unique user is worth to you. In which case your evaluation function is really VI, your sort of private value for showing an ad to a new user, times the public value summarization function, which includes the complicated logic of taking the union, the cardinality of the union. Okay, so like single parameter domains can encompass relatively complicated mechanism design settings. The key assumption, though, is that the thing that makes the valuation functions complicated is publicly known. And the thing that I don't know is just a single scalar. Okay, does that make sense? So from this point on, we're just going to like talk about single parameter domains. So I want to pause here. Like if these make no sense, this is like a really good time to ask for clarification. Yeah.
Have like the same sort of structure for each player?
Not necessarily. Yeah, these public value summarization functions could, in principle, be totally different for each agent. Now, probably in most realistic settings, you might not know, like you might know about the setting in general. I know in general, when I'm selling paintings, you prefer to get the painting than to not get the painting, and that in general, you don't care who gets it if it's not you. I might know a lot less about specific bidders. So it might generally make sense to model things so that these public value summarization functions are the same across all of the bidders, just because I'll know about the domain in general, but maybe not about the specific bidders. But this setting is flexible enough that if I did know something specifically about you, I could model you differently than everyone else. Yeah. So here, I guess, maybe it's what I called AIJ up here. Like the outcome is, like what I need to decide is which, say I've got a set of advertisers and a set of advertising slots, then maybe like XIJ is 1 means like advertiser I is the one that's assigned to slot J. And so to figure out advertiser I's utility, we would take the union over all of the slots J that are assigned to them of the set of viewers of that advertising slot. Yeah.
But if you the idea that the agent's valuation is described by a single number, if you have like able to describe by number, because you have like different numbers based on like I guess if you're doing advertising, like you don't want it to sell to the vendor.
So your utility function, there has to be this like publicly known public value summarization function. And then your utility function has to be describable as like a number, VI times this thing. So for example, when I write down this public value summarization function for a single item auction, this is the thing that is encoding the structure that you don't care who gets it if it's not you, because your relative utility is 1 if you get it, and it's 0 if you don't get it, no matter who else gets it. So writing this down, this is encoding the logic that your relative preference is first to get the item, next to not get the item, and you're indifferent between all alternatives in which you do not get the item.
Is it public in the sense that it shares that value function?
It's public in the sense that like I can design the mechanism with this knowledge. Like this is not this, right? Like in the end, we're going to ask for mechanisms that are dominant strategy truthful, which means there's something that is going to be in the strategy space of the bidders that they can report to us and possibly choose to misreport. I'm not going to ask them to report a whole valuation function, which is an arbitrary mapping from alternatives to numbers. I'm going to ask them to report a single number, which is like the scalar multiple of this thing, which is assumed to be their utility function. Does that make sense? Yeah.
But if you theoretically define the single item function thing as a 1 if A equals I, -1 if A is less than I, and 0 otherwise, and then it would matter for each player, like which other people get it.
Oh, so you're saying like you're imagining a setting where I like basically people come like lined up. There's people like left of me, there's people right of me. Like my favorite outcome is that I win it, next that the people left of me win at, next that the people right of me win at. Yeah, that would also be a single parameter domain. It would be a different one, but you could encode that as a single parameter domain. What you would have difficulty encoding as a single parameter domain is if each bidder could have uniquely arbitrary preferences over who gets the item. But if everyone agrees that there's this ordering and everyone is happier if someone to the left of them wins than to the right, you can also encode that as a single parameter domain.
Just to clarify, like if each person has like an NP that they don't want with the item, they have a negative one. If they're ending up the item, that would.
So long as I know who your enemy is, it would be. I can't because when I'm asking you to report something, it's just this number VI. It's not this number VI paired with who your enemy is. But yeah, you could have we could have a single parameter domain where your first favorite is, you get the item, your second favorite is anyone but your enemy, your third favorite is your enemy gets it. And I could encode that as a public value summarization function, so long as I already know who your enemy is and I don't need to elicit that from you. Does that make sense? Yes, so these are just 3 examples. You can encode all sorts of stuff as single parameter domains, but not arbitrary things. It is a limitation, but you can encode everything we've just mentioned. Good questions. Yeah. Yeah, the players know their own utility functions, so. They could, sure. Yeah, what we're gonna derive is mechanisms for which it's a dominant strategy to report the VIs, so long as we're in a single parameter domain. Okay. So everyone comfortable with this setting? Okay. So let's remember what a mechanism is. Remember, it is an allocation rule or a choice rule together with a payment rule. The choice rule or the allocation rule, right, it's a mapping from reported valuations, which in these single parameter domains are just, each reported valuation is just like a real number. It's a mapping from reported valuations to alternatives chosen. So in principle, a choice rule could be like totally arbitrary. It could map arbitrary reported vectors of reported valuations to alternatives. But we'll say that a choice rule in a single parameter domain is monotone, non-decreasing in the bid of player I if no matter what the vector of other bids is, no matter what the bids of the other players other than I are, and for every possible misreport that bidder I could consider making that is pushing their bid upwards. So for every VI prime that is bigger than VI, it should be that the public value summarization function of the alternative chosen when bidder I bids the lower value should be only smaller than the public value summarization function of the alternative chosen when bidder I bids the higher value. So this is saying, if you raise your bid, it might be possible that the alternative changes, but the alternative should change to something that you prefer, not to something that you like less. Okay, so if I, like in a single item auction, if at some bid I am losing the item, so my public value summarization value is 0, and I raise my bid, I can go to winning the item. So my public value summarization function might shift to 1 by raising my bid, but the reverse shouldn't happen. I shouldn't go from winning the item to losing the item by raising my bid. And more generally, my value, which up to scaling is just my public value summarization function applied to the alternative chosen, is monotone increasing in my bid, or at least non-decreasing. Right? I can't get an alternative that I like less by raising my bid. Okay, does that make sense? Pretty natural property to think about, that sort of if someone raises their bid, that should only cause them to get an outcome that they like more. Okay, Clear questions about this property? Clear? Okay, sorry. In a single item auction, this means if if our allocation rule is such that some agent wins at bid VI, he also has to win at all higher bids. Okay. So here is sort of the punchline. What we're going to prove is that within single parameter domains, if you have an allocation rule, and you're interested in the question of whether you can implement it truthfully, whether you can implement this allocation rule by pairing it with a payment rule that makes truth-telling a dominant strategy, you can answer that question by just asking yourself, is the allocation rule monotone in all of the bidders' bids? If the answer is yes, there is a payment rule that implements this choice rule in dominant strategies. And if the answer is no, there's not. Okay. So in particular, like here's the theorem. The payment rule is not even a mystery. It's like given here in the theorem. So a mechanism in a single parameter domain, by which I really mean, I guess, a choice rule. Okay, so you think about it this way, maybe. Like you've got some objective function you'd like to optimize for in a way that makes truth-telling a dominant strategy. Well, once you have that, if you're going to be able to do that, you know what the allocation rule has to be. It's got to be the allocation rule that chooses the alternative that maximizes whatever your objective function is, given the valuation function. Okay. Look at your alternative. Look at your choice rule, and check: is it monotone, non-decreasing in this sense? Is it the case that for every bidder I and for every set of bids, bidder I can only obtain a more preferred outcome if they raise their bid, never a less preferred outcome? Then, if that's the case, if you pair your allocation rule with this particular payment rule, then you'll have a dominant strategy truthful mechanism that implements your objective function of choice. And if it's not, there is no mechanism that implements your objective function of choice in dominant strategies. It's just not possible. Okay. And the payment rule is something, and maybe we'll look at this and sort of observe that it recovers things like second price auctions. But is the form of the statement clear? Okay, so it's like a complete characterization in single parameter domains of which objective functions you can implement truthfully and which you cannot. And the characterization gives a very simple answer. Like the allocation has to be monotone, non-decreasing in every bidder. All right, maybe it's worth just spending like a moment like glancing at the form of the payment rule that makes this thing truthful, and observing that even though it looks kind of complicated, it's got like an integral, it does recover like the simple things we've studied so far, like second price auctions in the sort of single item auction setting. Okay, so what's the payment rule? How much money do you have to pay? Well, you have to pay your value for the alternative chosen. That's what this is, right? VI, your value, times your public value summarization function, evaluate at the alternative chosen, minus this like integral over all bids lower than yours, all bids between 0 and what you actually bid, 0 and VI, of what your public value summarization function would have been had you bid this lower value Z. Okay. So let's just maybe like observe that this recovers a second price auction in a single item auction. Okay, so let's suppose that, I'm the winning bidder. I bid $100 for the item, and I won it. And the second highest bidder bid $75. Okay, so the payment rule, to be consistent with what we studied last class, had better be that I should pay $75. Okay, well, if I won the item, my public value summarization function at the alternative chosen is 1. I won the item, and we multiply by $100, my value for the item, so that's 100. And then I subtract off this integral from 0 to 100. Well, what's my public value summarization function here? It's just 1 for bids for which I win the item, and it's 0 otherwise. Okay. So it's just the indicator function for like the event that bidder I wins when they bid Z integrated over all Z from 0 to 100. Now, if I'm giving the item to the highest bidder, what is the lowest bid such that they win? Well, it's the second highest bid. At the moment that you raised your bid above the second highest bid, you became the high bidder. So whatever the second highest bid was, the integral from 0 to the second highest bid was 0, because you didn't win the item. The public value summarization function was 1. The integral from the second highest bid to the indicator was 1 everywhere from the second highest bid to your true bid. So this integral, right? We have 100 minus just the difference between your actual bid and the second highest bid. Your bid was 100, we said, of like the function 1. So it's just 100 minus v2, and the price you pay is just v2, the second highest bid. Okay, so this is some payment rule that's like, on its face, it looks a little more complicated than a second price auction. It's got this like integral in it, but as a sanity check, like when we instantiate this for single item auctions where the thing we want to maximize is social welfare, which just means give the item to the person who likes it the most, like gratifyingly, this complicated expression recovers second price auctions. And like more generally, we can take other domains and apply this payment rule and it'll recover other things. Okay, so is the statement of the theorem there? Okay, so let's prove it. And I want to simplify notation, because otherwise we have to like think about expressions that look like this a lot, like wi of x of z v minus I. I just don't want to write that down over and over again. So let's simplify notation in the following way. So like, first of all, what are we doing? We're proving dominant strategy truthfulness, for which means we're going to need to reason in the following way. We're going to have to pick a particular agent I to zoom in on. And we need to say, look, no matter what everyone else bids, it's always in bidder I's best interest to bid the truth, to tell the truth. And so throughout all of these arguments, we're just going to be fixing what everyone else bids and thinking about the incentives of agent I. So I want that to be reflected in the simpler notation as well. Okay, so choose your favorite agent I. Okay, just choose it right now. Also choose the bids of all of the other agents. The argument we need to make had better be true no matter what those things are. So let's just fix them. And now, when previously I would have written, w of x of v, where v is this vector of all of the other bids and bidder I's bid, and w is the public value summarization function, and x is the allocation rule, I'll just write y of v for that. Okay, and this will just be like, I'll think of this just as a function of bidder I's bid, fixing everything else. It's just, what is bidder I's relative utility, relative value, according to their public value summarization function when they bid B. Okay, so just for example, in a single item auction, fixing what everyone else bids, y of v is just 1 if bidder I wins the auction, and it's 0 otherwise. Okay, so this is just like simpler notation for like the thing we're going to need to be talking about during this argument. Does that make sense? Okay. Now we're proving an if and only if characterization, so we need to prove 2 directions of the claim. Let me prove one of them first. So what do I want to prove first? Well, right, the 2 directions are, on the one hand, if x is monotone, non-decreasing, and we use this payment rule, then the mechanism is dominant strategy truthful. That's the one I want to prove first. In the other direction, we're also going to need to eventually prove if x is not monotone, then no payment rule can make the mechanism dominant strategy truthful. Yeah. As I've written it, it does not say that, but that is also true. We're not going to prove the uniqueness, but it is true that this is the unique payment rule that does it. Well, this is the unique payment rule that makes it truthful and individually rational and budget balanced. Of course, if all I wanted was truthfulness, I could also take any translation of this, and it would work. Okay, so first we're going to prove the one direction that says, if you give me an allocation rule that happens to be monotone in the bids of all of the agents, then the payment rule on the previous slide makes it dominant strategy truthful. Okay. Okay, so like just again to like write down what we need to prove in our new notation to make sure we get it. We need to prove the following. Remember, you are bidder I. Your true value, unknown to the mechanism, is V. What we need to show is that you can't benefit, you can't get a higher utility outcome by misreporting some other bid V prime. Okay, so this is the inequality we need to show. We need to show that your utility, if you tell the truth, is higher, only higher, than your utility if you lie and misreport your valuation as V prime. What's your utility if you tell the truth? Well, it's a single parameter domain, so by assumption, it's V times Y of V minus the payment you need to make. Okay, both the allocation and the payment are a function of your report. What's your utility if you lie? Well, if you lie, you'll get a different allocation and a different payment, but you won't have changed what your actual utility is. So your utility will be V times Y of V prime. Like your utility will still be evaluated according to your actual utility function, but the alternative chosen might be different. And the payment that you have to pay could also be different. Okay, so dominant strategy truthfulness just means for all V prime, it had better be that V times Y of V minus the payment you make when you report V, that's just your utility when you tell the truth, is at least V times Y of V prime minus the payment you need to make when you report V prime, that's your utility when you lie. Okay, so this is just a restatement of what we need to prove in our notation. Clear? Okay, and like the theorem statement was nice enough to like actually give us an expression for the payment you need to make when you report V. So we don't need to like wonder what that is. We can just plug it in, right? Like the payment rule is this very specific thing. It's your value according to your reported valuation of the alternative chosen minus the integral from all the bids, the integral over all of the bids you could have made that were lower than the bid you did make of your the public component of your value if you had made those lower bids. Okay, so your utility, in that case, if you tell the truth, well, it's your value for the alternative chosen minus the payment you need to make, which subtracts off your value for your reported value for the alternative chosen, which is the same as the value for the alternative chosen if you told the truth, minus the integral over all lower bids of this thing that we're now calling y of z. And that had better be higher than your value if you lied, or your utility if you lied, which you really experience utility v times y of v prime, right? Because you lied, but you didn't deceive yourself. But what the payment rule subtracts off is your reported utility for the alternative. So what the payment rule subtracts off is now v prime times y of v prime plus, again, y of z integrated over all bid z that were lower than the bid you actually made. Okay, so this is just the thing we need to prove, but plugging in our actual expression for the payment rule. Okay, and just trying to simplify this a little bit. We might notice that we have this cancellation on the left, v times y of v cancels out with the same term in the payment rule. And so what we need to show is just that this integral on the left, this integral from 0 to v of y of z, this integral over all lower bids lower than your true value, had better be bigger than this integral from all bids lower than your reported value, minus v prime minus v times y of v prime. Okay, so this is just simplifying the expression. Okay, this is the thing we need to show. Okay. Now we can basically prove this by drawing a picture. That's what we're going to do. The only thing is there's two pictures we might need to draw depending on whether v is bigger than v prime or whether v prime is less than, whether v is bigger than v prime or whether v is less than v prime. Okay, because we're going to draw a picture that's the difference between these two integrals, and it's going to matter whether v is on the left and v prime is on the right or vice versa. Okay, so let's consider two cases. The first one is going to be the case when v prime is greater than v. Okay, so your misreport is bigger than your real value. In which case, if I subtract off this integral on the left-hand side from both sides, what I get left on the right-hand side is just the integral from v to v prime. Okay, and so the expression that we need to show simplifies to the integral from v, your true bid, to v prime, this higher misreport you made of your public value summarization function. Well, that had better be less than the difference between your misreport and your true bid times your public value summarization function at your misreport. Okay, so I claim that this is like a picture. So ignore everything else on the slide. I'm going to draw a picture for you. So we're taking the integral over this thing y of z, which is some curve. I don't know much about what it looks like, but I do know by assumption that it is monotonically increasing in z. That was the premise, right? Our allocation rule was monotone. So whatever this curve y of z looks like, kind of curving upwards. Okay, that was the one assumption we made: monotone, non-decreasing. Now I'm looking at the integral of this thing from v to v prime. And I know in this case that v is less than v prime. So let's say v is over here, v prime's over here. And so can anyone remind me, probably you all took calculus back in third grade or something, so it's been a long time, you don't really remember, but let's try to like how do I draw an integral? What is the geometric meaning of like a 1D integral of a curve? Yeah. Area under the curve. So the integral from v to v prime, like this thing that we need to bound, it's like the area under this curve. Okay, so the left-hand side is this area I've shaded in yellow. Now this right-hand side is like the product of two numbers. And I guess in like first grade Euclidean geometry, you talked about like areas of shapes. What kind of shape has an area that can be described as like the product of two numbers? Yeah, it's a rectangle, right? So what are those two numbers? Well, one is y of v prime. That's just this point here at the top of the curve. And the other of which is v prime minus v. That's just the length of this interval that we're taking the integral over. Okay, so the right-hand side is the area of this rectangle. Okay, and the area of the rectangle is bigger than the area under the curve because the curve is monotone increasing. Okay, the area shaded in white includes the area shaded in yellow. And that's what we needed, right? That the right-hand side should be bigger than the left-hand side. Okay, makes sense. And if you prefer algebra to pictures, it's also like a one-liner. Okay. Now there's this other case too, because if v is actually bigger than v prime, then this integral is going to be like negative. And in order to think of it as an area, we're going to have to multiply by -1, which is going to flip some signs around. So let's just do that case as well. If v prime is less than v, the thing we need to do simplifies a little bit differently. Now, the integral from your lower misreport to your higher true value of your public value summarization function at these bids z you could have made in between. Now this should actually be bigger than v minus v prime times your public value for misreporting at v prime. Okay, so let's just draw this picture a little bit differently now. Okay, so same axes, but now v prime is the smaller number. And v is the bigger number. And still don't really know what this curve looks like, but I still know it's monotone increasing. Okay. Now the left-hand side, it's still, like we've arranged things so that we're still integrating from the smaller number to the bigger number. Okay, this time v prime is the smaller number. So the integral can still be interpreted as the area under the curve. Okay, so the left-hand side remains the area under this curve. And the right-hand side is still a product of two numbers, so it's the area of a rectangle, but it's a different rectangle this time. So the width of the rectangle is still what it was before. It's the interval that we're integrating over. It's the interval from v to v prime. But the height of the rectangle is no longer the highest point on this curve over the area of integration, but rather the lowest point on the curve in the area of integration. So the right-hand side is the following rectangle, whose base is the interval we're integrating over from v prime to v, but whose height is now the lowest point on this curve that we're integrating over. And again, because the one thing we know about the curve is that it's increasing. We know that the area of the rectangle has to be smaller than the area under the curve. In particular, it misses like all of the area under the curve that corresponds to parts that actually increased. Okay, and so the area of the rectangle, the right-hand side, is only smaller than the area under the curve, the left-hand side, which is the thing we were trying to show. Okay, makes sense. So that's actually the complete proof in the one direction, right? We've shown, like, even though all we did was like draw pictures of curves on the board, like what we've shown is that if you pair any monotone allocation rule with the payment rule in the statement of the theorem, which remember recovers, among other things, the second price auction rule, then the resulting mechanism makes it a dominant strategy to tell the truth. Okay, so like simple geometric argument, that, monotone allocation rules can always be made dominant strategy truthful and with a particular payment rule. Questions about that direction? Okay, so we still need to prove the other direction. And like in some sense, you might think the other direction is kind of harder to prove because there's this sort of universal quantifier. Like in this direction, I told you what the payment rule is. And so in some sense, like the thing you needed to prove, inevitably, if it was true, inevitably had to come out of, just like manipulating the algebra. Because you knew what the allocation rule was, you knew what the payment rule was. So, there was a particular mechanism you were analyzing. You could just write down what your utility was for telling the truth, what your utility was for misreporting, and you just had to like establish an inequality on this particular mechanism that I told you was true. In the other direction, what we need to show is that if I give you a mechanism that is non-monotone, an allocation rule that is non-monotone, then there does not exist a payment rule that you can use to make it truthful. So it's not enough to show a violation of truthfulness for a particular payment rule. You need to show that for all payment rules, you don't get a dominant strategy truthful mechanism. Right, so this conceptually seems harder. We need to prove the non-existence of something rather than just establish the properties of a particular concrete mechanism. Okay, it's not that hard either. So let's do it. And actually, it's going to be a little bit easier to prove the contrapositive. So remember, the original statement of the theorem, this direction of the theorem, is that if your allocation rule is non-monotone, then there does not exist a payment rule that makes it truthful. But what I'm going to prove is the equivalent statement, which is the contrapositive, which is that if there is a payment rule that makes your mechanism truthful, then your allocation rule is monotone. Okay? So that's an equivalent logical statement, but it'll make it easier for us to think about things because algorithmically we can think that someone has handed us a truthful mechanism that includes an allocation rule and a payment rule. So now we can start reasoning about its properties with this payment rule. And what we need to establish is that whatever this mechanism is, the allocation rule has to be monotone. Okay, so that's like a logically equivalent statement, and it's the one we're going to establish. Okay, so to show, you hand me something that is you claim is a truthful mechanism. Okay, so it has an allocation rule. In particular, it defines this object y that we're talking about, and it's got a payment rule. And what I need to be able to do is look at this object you've handed me and hand you back a proof that your allocation rule is monotone. Okay, so what do I know? I know that I've got a particular pair of objects, an allocation rule and a payment rule, and I know that by assumption, the mechanism defined by these objects is dominant strategy truthful. What does that mean? Well, it means that if you tell the truth, your utility, which is just v times y of v minus p of v, the payment you have to make when you tell the truth, is only larger than your utility when you lie, which is just v times y of v prime, right? Your true utility for the allocation that results from your lie minus the payment you have to make when you report v prime. This is just, this must be, if the mechanism is dominant strategy truthful, this must be true for all pairs v and v prime. Okay, and in particular, it has to be true for pairs such that v prime is bigger than v. Okay, so without loss of generality, let's assume that the misreport we're talking about v prime is bigger than v. Okay, so this is just the statement of dominant strategy truthfulness when your true value is v and your misreport is v prime. Now, if a mechanism is dominant strategy incentive compatible, right, like it has to be a best response for you to tell the truth no matter what your value is, right? Like it doesn't make sense to say the mechanism is dominant strategy incentive compatible if your value for the good is exactly $2, right? Like what it means for the mechanism to be dominant strategy incentive compatible is that no matter what your true value for the item, it should be a dominant strategy for you to tell the truth. So in particular, right, like this is the world, this is the statement of dominant strategy, this is the implication of dominant strategy truthfulness when your true value is v, and you're considering misreporting v prime. But you can also consider the world where your true value is v prime, and you're considering misreporting your bid as v. And that also should be a bad idea if the mechanism is dominant strategy truthful. Okay, so let's suppose that in this, bizarro world, your true value is now v prime, the thing that was previously your misreport, and you're considering whether you should misreport v, the thing that in the bizarro world was your true value. Well, in this case, dominant strategy truthfulness requires that misreporting is also a bad idea. So your value if you tell the truth, your utility if you tell the truth, which in this bizarro world where your true value is v prime, is now v prime times y of v prime, your true value for the alternative chosen, minus the payment you have to make when you report v prime. Dominant strategy incentive compatibility requires that this is larger than in this bizarro world what your utility would have been for misreporting, which is your true value in this world, v prime, times the allocation you get when you tell the truth, minus the payment you get when you misreport. Okay, so this is possibly, like we're basically done. But let me pause here, because even though these are these inequalities are both just reading off an implication of dominant strategy incentive compatibility, this is possibly like a slightly subtle step where we're saying, look, dominant strategy truthfulness means you're better off telling the truth whether your value is v and you're considering misreporting v prime, or whether your value is v prime and whether you're considering misreporting v. Is that clear? Yep. It's not the same because, but like, note that when you misreport, you evaluate your utility according to your true value. You haven't deceived yourself, just the mechanism, but according to the allocation chosen by the mechanism. So here, like the cross terms, here we have v times y of v prime. This is what happens when you really value the thing at v, but you misreport v prime. The corresponding thing here is v prime times y of v. Okay, so these are different statements, but both statements that are implied by dominant strategy truthfulness, because dominant strategy truthfulness means it's a good idea to tell the truth no matter what your value is. Does that make sense? Okay, so this is the main idea. Is this step clear? So both of these things have to be true if the mechanism is dominant strategy truthful. So whenever you have like two inequalities that are both true, it is very tempting to like add them together. Like if A1 is greater than B1 and A2 is greater than B2, then like another true inequality is that A1 plus A2 is greater than B1 plus B2. We've got two such inequalities here. Let's just add them up. And what's going to happen when we add them up? So the first thing we might notice is that there's going to be some cancellation. And in particular, all of the payments are going to cancel, right? Like, because on the right-hand side here, we have the payment you have to make if you bid V, as if V was a misreport. But on the left-hand side up here, we've got the payment you have to make if you bid V. Here, V was the truth, but the payment rule doesn't care. The payment is the same. The payment's just a function of the bid. So the payment terms when you bid V cancel out when you add these two up. Similarly, the payment terms when you bid V prime cancel out when you add these two equations up, which is good because the thing we're ultimately trying to prove is a statement about the allocation rule. It has nothing to do with the payment rule. Right? We're trying to prove the allocation rule is monotone. So it's a good, like it's sort of annoying that these dominant strategy truthfulness statements conflate the allocation rule with the payment rule. But by adding these two inequalities up, we cancel out all of the terms corresponding to the payment rule. And so what's left? Well, we just get that V times Y of V plus V prime times Y of V prime is at least V times Y of V prime plus V prime times Y of V. Okay, this is what is left after the payments cancel out. And we can combine like terms, right? We've got like Y of V terms on the left and the right, and we've got Y of V prime terms on the left and the right. So combining like terms, we've got V prime minus V times Y of V prime, just aggregating together the Y of V prime terms from the left and the right, is larger than V prime minus V times Y of V. And remember, V prime is bigger than V. That was the assumption, right? Our initial presumption was your value was V, and you were considering a misreport at a strictly higher value V prime. So V prime minus V is some positive number. And so we can divide both the left-hand and the right-hand side of this inequality by V prime minus V. And what we've established is that Y of V prime is bigger than Y of V. And the only thing we started with was the assumption that V prime was bigger than V. Right, so we've just established that if V prime is bigger than V, then Y of V prime had better be bigger than Y of V, which is exactly the monotonicity property. Okay, so if you handed me a truthful mechanism, irrespective of what the payment rule was, the allocation rule had better be monotone. So that completes the other direction of the characterization. Right, on the one hand, if you have some arbitrary objective that leads to a monotone allocation rule, you now know how to make that truthful. You don't have to worry about thinking about payment rules and proving dominant strategy truthfulness anymore. You just need to check monotonicity. You can look up what the payment rule is from this slide. On the other hand, if the thing you want to implement doesn't have a monotone allocation rule, if the corresponding allocation rule is not monotone, you don't have to waste your time thinking of payment rules trying to make it truthful. You now know it's impossible. Okay, so we've, in some sense, reduced what was originally a mechanism design problem, right? Simultaneously come up with an allocation rule and a payment rule to choreograph incentives so that people want to report truthfully, into what is now like a purely algorithm design problem. Just design a monotone allocation rule. Okay, and the mechanism design part is handled by this theorem in sort of a black box way. Okay, questions about that? All right. So in that case, I'll see you guys next time when we'll start putting this characterization to work.
Can you quickly refresh on what monotone means in context of this